This, and the other learning resources in this course have been made possible by funding from the European Commission's Erasmus Plus program.
Good afternoon, good evening, or good morning, everybody. Today I have two topics to be for discussion. First topic will be on point cloud filtering or point cloud classification. And after the break, I will tell you a little bit about the point cloud deliverables. So with the tools that we have seen now with Cloud Compare, what you can do to make your point clouds as a real deliverable for also for non-expert people, or for people that have not the ability to work with dense point clouds. And I will mainly focus here on the construction of digital elevation models. Tomorrow is formally the last day of this part of the summer school, of this module on laser scanning. And for tomorrow, I would like to discuss about JavaScript-based point cloud visualization. So PO3. I will show you again how to start your local server and then how to convert a LAS file, so a laser scan point cloud, to something that is readable in your browser. I think it's very useful also if you have a big project and you have some point clouds available in your project. Then this is a wonderful opportunity to share the point cloud with the public. And I will also show you some examples of an implementation of that. But for now, we will discuss about point cloud filtering. And once again, if you have any questions, feel free to interrupt me or to ask your questions. Voila, let's go to the presentation. I will keep an eye also on the chat and on the people that might attend a little bit later. So now we are here in point cloud filtering. So you've most probably seen, if you work with point clouds, or if you're working with laser scanning data, that you're not only measuring your environment in terms of geometry or in terms of RGB values or intensity values, but you're there's something going on. Oh, dankjewel, schat. Dankjewel. You're not only measuring your geometry, but you're also measuring a lot of erroneous data, erroneous points, and redundant points. You see it here as an example. For example, this is a screenshot taken for the data that we will work with in the demonstration, and you see some erroneous points. So we have to identify these points and eliminate them from the point cloud. So in most cases, before you start really working on your final deliverables, like architectural plans or digital elevation models, it's a very good idea to eliminate these erroneous or redundant points out of your point cloud. So we need point cloud cleaning and data reduction to facilitate that process. And then we're talking about the removal of noise, so just scattered points that are definitely not useful for our data set. We are talking also about moving objects. I was not involved in the data acquisition of this point cloud. It's the point cloud of Eleusis in Elefsina, but most probably this cloud that you see here is a moving object, is a person walking while the scanner was scanning its environment. And these are obviously points that have to be removed. Also, if you would go back, for example, to the point cloud that was measured of the syntagma square in Nafplio, in that case, we are measuring in the middle of the day, so people are having their coffees at the terrace, they are walking for shopping, you have tourists walking around. So all these objects are actually objects that are not useful in the point clouds. They are erroneous or redundant points that have to be removed. And also other artifacts. So artifacts that are definitely not wanted in that case. For example, if you measure a mirror using a laser scanner, you will also find a lot of erroneous points, or metal objects also have this tendency of resulting in a lot of erroneous points. Also data overkill, especially when you're working with a terrestrial laser scanner and you're making a full 360 dome scan of your environment. Most of the time, you're only interested in a small portion of your scan. Let me go to my data. Here in the for the Lierde project, so the project I've been working on. I will take let's take this scan here. Go to Cloud Compare, just to give you an idea what I'm talking about. In this case, I was only interested in one particular building, or the municipality asked me to measure one particular building. But of course, I measured a lot of features around that building too. So these are obviously artifacts caused by the sun illumination. Let me go to the RGB values. So in this case, I'm only interested in this building here. Ooh. Voila, only in this building, but I'm making a scan of a full dome. So I also have the neighbor and I have some other residential buildings over here. And of course, the targets are also scanned in a lot of detail. So I need ways to only extract this part of the building on the one hand. And I think in this case, there are also some objects available that are definitely noise. There was, I think, a guy walking here. There was another one on a bicycle. So in that case, you will see a very scattered point cloud that obviously has to be eliminated. So we're talking about the removal of noise moving objects, but also data reduction in terms of overkill, because we are only interested in a small portion of the area. We want to focus on that area, and maybe I don't even need the original resolution of my data. So I don't need this sub-centimeter point density, but maybe I can reduce my point density to a certain number. Ah, het is goed meisje. Dankjewel. Oh, dankjewel. The approach of filtering these point clouds is in general, but this is not always the case, but in general, it will differ for airborne laser scanning data and terrestrial laser scan data. Dankjewel, schat, dankjewel. Ik zal hem overpakken. It's Wednesday. Yeah, it's Wednesday afternoon, so my daughters are at home. So in general, I would say that if we're working with airborne laser scan data, we're working in a 2.5D approach, so actually the same approach as what you would have with when working in a GIS. And in terrestrial, with terrestrial 3D laser scanning, we're working in a 3D approach. So in that case, we also have to work in terms of filtering with our 3D, in our 3D environment. Zou je Anne kunnen meepakken, alsjeblieft? What does it mean if we have our actual terrain or we have our actual object? Like for example, here a cross section of a gully in this case, or if I go back here to my original point cloud where I have my my building. So here's my my building again. In this case, of course, I have a full 3D representation of my object, my actual object, and it also means that I have a full 3D representation required, because for one XY position, so for one planimetric position, I have in this case 1, 2, 3 altimetric positions. And if I want to make a model of the actual terrain or my facade or anything like that, in a full 3D, I have to make, of course, a representation that is compatible with that geometrical representation. Whereas if we are working in most airborne applications, not necessary, but commonly when we're working in airborne applications, we will actually have a 2.5D representation, and that means that the elevation, our Z parameter that you see here, is actually a function of my planimetry. And it also means that for one position, I have one and only one altimetric value assigned to it. So that's what you see here. And for, I'm sorry? Lorendo? There was a question?
No, I think Lorenzo has forgotten to mute his microphone.
In that case, Voila.
Can you, yeah.
So it actually means that if we want to make a model where we take into account these types of undercuts, or where we want to work with the interior windows or the window construction of an architectural monument, the 2.5D is definitely not suitable. The big advantage of this approach is that it allows us to make very simple analysis on the resulting digital elevation model. So with the digital elevation model, we have a raster. Each and every cell in that raster has an elevation assigned to it. And it is very easy from a computational perspective to perform raster-based analysis on it, whereas these are much more difficult and computational intensive when you would do that in full 3D. Another thing that I would like to stress out is the distinction between filtering versus classification. In filtering, or when speaking about filtering, we're actually making the distinction between true points and false or erroneous points in our point clouds. So the noise, the moving objects, the artifacts, these are considered noise. They do not contribute to the point cloud and to our research question that we are asking. Whereas when working with classification, we're actually assigning classes, so an object identifier, to points. So for example, here I have this airborne point cloud that I will also show you in a few moments again. I have an airborne point cloud, and I can use automated algorithms to say, okay, please make a distinction between ground points and non-ground points. So here we have the ground points for that area, and we have the non-ground points for that area. Or you could say, no, give me the ground points, and within the non-ground points, make a distinction between high vegetation, low vegetation, buildings, and other stuff like that. So then we are talking about classification, the distinction of points based on classes. So it's actually some kind of a semantic model that we can build on top of our point cloud. Then another very important question to ask is, when will we apply our classification or our filtering? But it's actually just before or just after the point cloud registration. Yesterday we spoken about point cloud registration, making our point clouds from different scans, for example, spatially coherent. So we will have several scans, we will register them, so we will make an alignment between the different point clouds, and we will end up with a massive point cloud combining all the different scans. And in that case, it's actually possible to do it before the registration, which will has some significant advantages. The first is that we will have immediate data reduction. So from the start of our data processing, from the start of our registration and all the steps that will come afterwards, we can already work with a reduced point clouds, meaning that we can only focus on our study area or only focus on the objects that are definitely not erroneous or part of the noise, which will obviously involve better performance accuracy, and in some cases also in better registration results. So for example, this does not hold for the target-based registration, but if you're working with a cloud-to-cloud registration and you're having moving objects or noise in your data, there is a possibility that the cloud is actually aligned based on these noisy data or moving objects or artifacts. So especially when working with cloud-to-cloud registration, it is a good thing to do some pre-filtering or filtering of your point clouds. However, on the other hand, it also or it might result in a loss of useful information for the registration. So if you're only focusing on your study area, then you will have a limited amount of data also for the cloud-to-cloud registration. So it's some kind of a trade-off that you will have to make here. Maybe only remove the artifacts and the noise and not remove the points that are not belonging to your study object. Another option here is to do the registration and filter your point clouds afterwards. Now, obviously, that is more computational intensive, and your registration, especially when using cloud-to-cloud registration, the noisy data may be included in the registration itself, so that's a big disadvantage of it. However, you will have the ability to filter your entire point cloud, so all the merged point clouds at once, especially when you're doing manual filtering. Instead of doing the manual filtering on 6 point clouds, for example, you can just do everything at once, and it may save you some time, and you can work directly on the final point cloud, or the registered point cloud. So what to choose? I think for cloud-to-cloud registration, it's better to do it afterwards, just some pre-filtering and then the thorough filtering after the cloud-to-cloud registration. If you're working with a target-based registration, of course, you will have to keep your targets in the point cloud, but then you can also do the filtering before the registration itself. So yeah, manual, automatic, and semi-automatic. We're now somewhere in the middle of registration and modeling. Actually, depends on if you do it before or after the registration. But still, we will not have the ability to have full automatic processes. Also here, we can do it manually, automatic or semi-automatic. And I will show you some of the approaches in Cloud Compare. If you do it manually, actually, you have already seen something like that. The most convenient way of filtering your point clouds, to say, okay, you're interested in a certain study area, is just make a manual clip of your study area and say, okay, we make a polyline or polygon, and we keep all the points that are situated within the bounding box that we draw here, or have all the points that are within the polyline or polygon that we have drawn in our point cloud. And it will not only allow you to clip your study area, but this tool is also very convenient and very straightforward if you just want to eliminate some of the manual points. If, for example, you're working with airborne laser scan data that is already referenced, this is a very convenient way of removing a lot of points that are out of scope or out of your study area. So for example, in this case, if I'm only interested here in these trenches, for example, the data reduction here goes from 2.5 million to 300,000 points. So that's quite a reasonable data reduction that we can do there. When we're talking about automated procedures, there are actually 3 approaches that I will show to you today. The first is a geometric constraint. So geometric constraint where we say, okay, we are looking for clusters, we're looking for features that have certain geometrical properties, and we will link these the points or consider points as being non-noise if they belong to a certain geometrical constraint. We can also use statistical parameters. So let's say, for example, we have a mean slope or a mean surface for a certain neighborhood of points. Then we can say, okay, if there are outliers, statistical outliers, we consider these outliers as noise, and we will just eliminate the noise. And also here, if you're more involved in statistics, there are different approaches that you can use. But only one, unfortunately, is applied in or implemented in Cloud Compare. So we will only use the standard deviation related to the mean of our elevation value. But of course, there are other statistical approaches that you can apply here, and I will end with that at the end of this presentation. And feature correlation. That's not about clusters, but that's more about real geometrical properties that you will try to fit with your point cloud. So, and semi-automatic, so that's somewhere in the middle in terms of performance. It's actually a combination of the above. In this case, we say, for example, okay, we have a mean surface. So let's take a point cloud here. This is the a part of the Elysis point cloud. We make a mean plane through the object, and we can calculate the distance of each point to this main object. And then based on these distances, we can actually work with threshold values. Let's say, for example, okay, we consider all the points that are further away than 1 meter, so -1 to and lower, and +1 and higher. We consider that as noise. We will eliminate that using Cloud Compare. And all the points that are left are considered non-noise. Actually, this method is frequently used, or actually I use it quite often in an iterative approach. So if I have a plane, I try to fit a best fitting plane on a raw point cloud. I say, okay, I have 1 meter above, 1 meter below. I remove these points, I make a new plane, remove 50 centimeters, 25 centimeters, 10 centimeters. So you can actually apply it in an iterative fashion to increase the quality of your point cloud by doing that. So we have talked quite intensively about the data acquisition process and the site preparation. It was mainly also for yesterday and the days before yesterday. We've talked a little bit about scan registration, and then here we are talking about cloud filtering. Also, when we are talking about the classification process, or segmentation, if you want to call it like that, we are also in the process of making deliverables. So classification and filtering are heavily related to each other, as you will see in the demo. But classification is part of the deliverable generation, whereas filtering is really about the preparation of the data before you can start making your deliverables. So in the demo that I will send you, I will work, of course, again with Cloud Compare. The data that we will be using are measured and acquired by Heritage using Leica C10 scanner. And on this site, they have measured a huge amount of points, and with a lot of scanning from a lot of scanning positions. I can show you again the entire point clouds that we are working on. Let me see. PC. So if I take, this is even the reduced point cloud that I'm going to show you with only 1 centimeter equidistance. So if you're familiar with the site of Eleusis, we are now in the same viewer that you will implement tomorrow. So we're really looking at millions and millions of points at the moment. In this point cloud, you still see some artifacts. So these are the signals received by the sun. In this case, you see some power lines, and we will be working mainly on this area. So I made a cut of the, I don't know the correct name. Maybe Vasya can tell it. What is the name of? Okay, do you know the name of this area?
Are you talking about the building? It's the Telesterion, I think.
Ah, okay. Okay.
Yeah.
I'm not an archaeologist, as you know, but thank you for clarifying that. So it's this area, and made an extraction of that, and you can also find it in the under the demo data that we will be working on. All these different scans are acquired for Heritage. If you zoom in a little bit, maybe zoom in. Maybe you can even see some, yeah, voila, here you see a scanning position. There are multiple scanning positions visualized by the difference in contrast. It's a huge work, very impressive what they've done here. And the cool thing is that it is accessible using a browser like this, also with some map viewers that you can see here. So you will familiarize yourself with that by tomorrow. So these are the data, and I will show you how to process these data in Cloud Compare. And for your information, I will also give a small note on the use of PDAL, which is part of the same suite that you downloaded for QGIS. So manual filtering. For your information, I give the different steps here for manual segmentation. So for example, if we go to, let me eliminate this point clouds. If I go to Cloud Compare to this site, for example, here, there's some noise in the data. You can also see that there's noise based on the bounding box normally. if you really see that the dimensions are totally out of scope, like for example with this point clouds, the Naflio data. If I go to the Naflio data, let me take it. It was about illustration. If I take, for example, this point cloud, and I look at my bounding box, then you see that this is definitely my core area, but apparently also here there is some noise in the data. So in order to filter these points or this point cloud, let me take the shader for point cloud visualization. The most convenient way of doing that is just selecting your point clouds, go to segment, and then you can draw a line around your study object. So let's do it like this. Voila, right click when you're finished, and then let's say you want to keep all the points that are inside this polygon. And if we are happy with that, we can just click OK. And you will have 2 points, the remaining with the erroneous points. So this is still the points that are far outside of our object. And we have our points belonging to the square itself. And the interesting thing, we can just remove this point cloud, or we can disable it. And then it's much easier to work with it, to work with the point clouds. Obviously, another way of another reason of using that tool is to eliminate small portions of the point cloud where you really say, okay, this is not relevant, or these are moving objects. You can just make your polygons around the object, eliminate them, and they will put in the remaining folder. In the remaining folder. And you can retain the segmented toolbox or the segmented point clouds. There was a question or a raised hand from somebody.
It was me, I'm sorry.
Yes.
Yeah.
Okay, it was not a question.
Yes, it was by accident, I'm sorry.
Oh, no problem, welcome. So this is actually quite a convenient tool to work with for manual point cloud processing. The problem what you will find is that if you have a point cloud and you start zooming in on an object that you want to remove, for example, here I see something that is definitely not wanted in my point cloud. This object, for example, is that it is actually as good as impossible to make a polygon around this object without also eliminating points that actually belong to the correct point clouds. And that's another reason why I would make segments using this tool here. And I will show that in one of the next slides, where we can actually use these segments to segment our point cloud and filter our point cloud segment by segment. This is actually a technique that is frequently used also for the processing of bathymetric data. So very useful. You select your point cloud, go to segment, and then you can make your polygons, select what's inside, select what's outside, and keep or remove points that are not belonging to the correct point cloud. So here for the cross sections. So let's say, for example, okay, we have here our point cloud with the far outliers totally removed, like this, for example. And let's make some segments here. So I go to cross sections. I will rotate my z-axis a little bit. And then I say, okay, let's make our first section, for example, let's say here. This is a little bit annoying because the Zoom screen is blocking my view. Let's do it like this. And what I can do now is say, okay, I want to export multiple slices. in what direction do I want to repeat my process? Let's put it in the Y direction. You can actually do it in all the 3 directions. That's totally fine, of course. Extract your contours, also slice per slice. It's something we discussed, I think on Friday, on Saturday, if I remember correctly. And also you can keep an area open. So make a slice, have an open space, slice, open space, slice, open space. But in our case, since we're aiming at filtering point clouds, we will not do that. And I will just keep it on 0. Make it a little bit larger, like this. And then I will slice my point cloud. So now in the green direction, it has apparently generated 12 slices. So the result is the same as what you would see with the original point cloud. But if I disable or devisualize my my original point cloud, and I will hide all the different slices except one, then you will actually see that I have the different slices here. Well, why is this so interesting? Because if I go back to this artifact that I just saw, I think it was not here, but also not here. Yeah, I lost it. No. Voilà. If I go to this artifact, in this case, it is very easy just to select that point. Oh, voilà. It was not an artifact. I think I just lost it. So let me go through the to the slides and try to find it again. I've already cleaned it enough. Let's say, for example, just to give you an idea, if I want to eliminate this lamppost on the original point cloud, that will be virtually not impossible, but very difficult, because I will have points that belong to the facade, or I will have points that belong to the surface. And what I can do in this case is just say, okay, I have my slice here. Let's select my slice. I go to my segment tool, and I can make a boundary around this lamppost. Keep everything that is outside. Do the same here for, unpause it. Let me do the same here for this lamppost. Keep everything that is outside. Even the tree I can eliminate. Especially for trees, it's very useful to use this technique. So let me take all the points that belong to the tree here. Voila. And if I'm ready, I have, of course, a segmented and a remaining. So these are the segmented or these are the remaining. And this is, let's say, our cleaned point cloud. And after doing that for all the different slices, all the different sections, you can just select those slices again, one by one.
Cornelis.
Merge them into one new point cloud.
Excuse me, I can't see your screen.
You cannot see my screen?
No. Can the rest of you see the screen?
Oh,
No.
Yeah, thank you for notifying that. The problem is, okay, on my screen, the menu bar was on top of my screen, so it was just interfering with Cloud Compare. So I will go back. Sorry for the inconvenience here. Where have you missed me? No, I will just make my slices again. Make them a little bit smaller. Make our multi-slice in the green direction. Apparently I have 9 slices now, but it's not that important. I will disable my master point cloud, and then we will look for, let's say, all the points that belong to the tree here. So voila, that's this point, this segment, and let's say this segment. I will go to the tree, zoom in a little bit on the tree. And now by using our slices, I can easily eliminate the tree without removing any points that belong to the facade of the museum or any of the buildings around the square. So let me draw the boundary. So this was a remaining point. This is a remaining point. This was outside. So I will just remove this one, and this one. Remove, and all the rest. Can be merged or fused. And the result of that is that we have our tree eliminated from the building. So we only have left what is behind the tree in this case. Without making these sections, it is impossible, or at least extremely difficult, to eliminate objects like that. So if you're not interested in our case, for example, a tree in front of a building, I would definitely recommend you to work with these slices or the segments for data cleaning. So that's actually what is expressed here, also step-by-step procedure, and again with some different screenshots. So yeah, this will allow you to, on a slice-based or the section-based data cleaning, that you can also apply on like the demo data or the data in the exercise. So now we can go to automated data filtering. We can imagine that manual data filtering is quite labor intensive, especially when you're working with very complex sites. For example, like the site on Eleusis. A couple of years ago, I received a question, okay, Cornelis, can you please filter this point cloud? I think it was like almost a billion of points included in the entire point cloud. So that was massive. And in that case, it was very useful also to apply some automatic filtering techniques on the point cloud itself. And one of the first straightforward techniques to apply here in this perspective is the statistical outlier removal. And the statistical outlier removal, what it does, you take your point cloud, it will take a point from the point cloud and it will look for its n neighbors in the point cloud. So in our case, or in this case, in the screenshot, it has 6 neighbors. So you take your point, and it will look for the 6 nearest points in that area, and then it will calculate the mean value of the elevation, and it will calculate the standard deviation of the elevation. And assuming that our noise, because we're here talking about noise, has a normal distribution around the mean, it also means that if we are far away from the mean elevation of a certain object, that we can actually consider that point as being noise. And that's here what is happening with statistical outlier removal. This is not a very useful technique to implement when you're working with hardcore 3D data. So 3D data of a facade, for example, because under normal circumstances, it will only consider the Z value, so the Z value, the elevation value of your point cloud. But this is very useful if you're working with bathymetric point clouds, with airborne point clouds, or with point clouds where you have a facade, but the facade is put in, on a flat plane, like what we did in when talking about the photoparametric project in Ghent. Another very important thing here is that since we are using a multiplier of sigma, so n sigma, it also means, and then I go back to this illustration, it also means that I always consider a certain amount of data as noise, even if it's not noise. So for example, if I say, okay, I take 2 sigma, it will calculate the mean, and it will say, okay, I have a mean, I have a certain standard deviation, and as soon as the elevation within that neighborhood is larger than 2 sigma, which is actually 95% of 5% of all the points are further away than 2 sigma of your mean, then these points are eliminated. So you will always, especially when your data is already going to getting cleaner and cleaner, you will always eliminate points. If the point cloud is perfect, you will always eliminate 5% of these points. So that's happening here in the statistical outlier removal. Why is this still very useful? Well, especially when you're working with data where there are a lot of outliers present in the data itself. So for example, in the ELUSIS data, this is terrestrial data, but it is acquired as if it is airborne data. So we have a topographic coverage of a very large site. And it will actually allow you to do some data reduction and to do some pre-filtering, or some interesting pre-filtering on the original data set. And you also see here, if I take my original point cloud that has been published also in the data repository, contains 26.3 million points. If I take 2 sigma as a value here, so 2 sigma, I will have 25.4 million points in my final point cloud. And if I take 1 sigma, I have 24 million points in my final point cloud. So this sigma value is actually quite important also as some kind of a threshold value to say, okay, what points are noise and what points are non-noise. But in any case, it will always remove a certain amount of data. So you have to be very careful with this technique. Another very important and very interesting thing to apply, and this is on the other hand a technique that I frequently use a lot. It's not proper English, but I use this quite often. It's connected component analysis. A connected component analysis will actually look for clusters of points based on a certain distance. So it will look at the entire point and it will calculate certain distances related to the octree of your data, so the base structure of your data. And given a certain threshold value, like in the screenshot here, it's level 8, and the level 8, according to this point cloud, has a step size of 35 centimeters. And if the distance is further than 35 centimeters, it will consider a certain amount of point as a cluster. And what is a cluster in that case? That is a point cluster, or a series of points that are within 35 centimeters in this case, and that have more than 10 points available. Well, let's implement that technique here on our ELUSIS data, because this is very interesting. I will try it here for the ELUSIS data. You will see, for example, here these white lines belonging to the sun. And there are also, if you look a little bit more closely, let me remove this and set my shader or use my shader. You will also see some noisy data that are left and right in the point cloud itself, like here and here. And let's try to automatically eliminate this, these artifacts using connected components. So that's here. Just for your information, this is our statistical outlier removal. And this is our connected components. I am able to play with this value, so I can be very strict, extremely strict even, and I can be very coarse. So this is really for heavy outlier removal for far away points. This is the default value, point value 8, but let's take level 9. And also we will say that if there are 20 points in a cluster, then it should be labeled as a cluster. What it does now is it will look for components, for connected components, and it will label label all the individual components. And the result of that is actually quite fast. What's happening here? The result is that I have found, or the computer has found 24 clusters. Of course, I have my main cluster, the biggest cluster, which is my topography in this case. And the rest of it is a lot of noisy, or I consider it as noisy data, or at least individual or isolated clusters of points. A very good question in this case would be, now, okay, what is then the relevance of this threshold value, the value that you had to, that I pointed here? Well, that would be a very good question, because this value will also tell you if there are clusters detected in the point clouds that are further away from another cluster than this threshold and the octree level. And if the number of points is less than, in this case, 10 or 5 or 25 or 50, all these clusters will be eliminated and all these points will be eliminated. For example, if I remove this result and I say, let me be very strict now. I say, okay, I go to a level 10 and I say a cluster should have at least 100 points. I hope this goes very smooth because it's the first time that I'm being so strict. What you see here is that, let me eliminate all these points. Voila. Now I've been very strict. And if you compare, this is my original point cloud. This is my original point cloud. This is the filter point cloud. So you see that already by having a few clicks using this connected component analysis, I've already been able to eliminate quite some points. So for example, here there were artifacts, here there are some artifacts, all these isolated group of points that have less than 100 points in a cluster, they're actually eliminated now. So it's quite a convenient way of point cloud reduction. So that's connected components. A last way that I would like to discuss with you is the ability to use these distance measurements or distance measurements from the point cloud to a certain reference plane. I'll also show it to you using, let's use the filter points here, filter point cloud. What you can do in that case, but it's not that convenient for irregular surfaces. But let's consider this as a regular surface. What you can do in that case is say, okay, let's create a best fitting plane, or let's create a mesh. So now here I have my mesh. And what you can do then is you can select the plane, select the point cloud, and then calculate the projected, or measure the projected distance from each point to the plane. So voila, here is our point cloud with a color assigned as a function of this distance value. And then by looking at the histogram, so let's select our point and look at the histogram. We can, for example, say, okay, let's consider all the points that are between 3 -3 and +3. Let's consider that as correct points. Now I have to be careful, but because I just closed my share connection using this button. So -3 to 3. You split my values. And then here I have 2 point clouds. A point cloud with all the points outside my, my threshold value and points that are within my threshold value. And of course, if you do that for a flat surface, even before doing your connected component analysis, it's quite an interesting way of doing a filtering, an automated filtering on your of your point cloud. So cloud to mesh distances can be very useful, not only for change detection and for deformation monitoring, but also for point cloud elimination and point cloud filtering. So here again, you calculate your mesh, you calculate your distances on that mesh. Using the histogram and the statistics of your histogram, you can filter by value and extract certain portions on that value. Then the last thing is just for your information, the pre-last thing, because I'm now thinking about something that I also want to show to you, is filtering using PDAL. PDAL is something that we will not discuss here too much in this presentation, but if you are a little bit into scripting, and if you are into GIS, you might or you might not have seen PDAL. So PDAL is an abbreviation of Point Data Abstraction Library, and it's actually a library of tools, different tools that will allow you to do point cloud filtering, point cloud classification, point analysis on using scripts. And this is actually installed, or you have the ability to install it if you are working with OS Geo for Windows. So for example, if I go to OS Geo for W in the shell. So if you have participated in the specialist course or the module on GIS, you probably have installed this one as well. And if you here type PDAL, you will find the different tools that are available in the PDAL library, or the different tools that are that you can use. Just for your information, when is this very useful? If you have a huge amount of points in your library and you want to do an automatic data filtering, you can just write your own scripts and say, okay, I will sequentially process all the files one by one using this PDAL library. If you don't have it installed, you can just go to the installer of OS Geo 4W, and then you can select the PDAL library. However, it is also possible to install it using Anaconda, for example. I'm a heavy Anaconda user for Python scripting. And if you're a Mac user, the PDAL libraries are also available via Anaconda. So if you have Anaconda, install PDAL and you will have your library. But that's just for your information. Know that it's possible. Like, to give you an example of the power of this, most probably you've seen that Cloud Compare is very powerful, but if you want to process more than, let's say, 50 million or 100 million points, your computer starts having difficulties with processing these huge point series, point clouds. A couple of months ago, I had a project where I had to process 1 billion of points. So let's say 1,000 million points, to put it like that. That was, at least for my laptop, it was impossible to do that in Cloud Compare. So I wrote a script in PDAL, and PDAL allowed me to process these data automatically. So it was just a matter of pressing enter, and the day after I had my my processed data set and point clouds that I could use for further data processing in QGIS and AutoCAD in that case. So extremely useful, many options. And one of the advantages here is that you don't have a graphical interface. So all the resources that would normally go to the interface are directly put in the processing of your data set. So that's something that I would like to, just for your own information. And also, last but not least, just before the break, I think I still have, well, I have a few minutes. If you are ever going to work with airborne laser scan data, if you're, by the way, interested in airborne laser scan data and you're working in Europe, you will find the INSPIRE data sets very useful. INSPIRE is a framework for spatial data interchange. Most probably Doc has also already informed you about it. So it's a directive that that forces all the member states to share data in a systematic way, or at least the metadata on these data in a systematic way. And one of these data sets are airborne laser scan data, which are freely available, at least in the Flemish region in Belgium, but also in the Netherlands, but in France or in Germany, you will have to pay for these data. So it's not always per definition for free. But in any case, I have a point cloud here. Already showed you this point cloud with some topography, with some trees. Let's assume that we want to classify this this point cloud. Then there is also a very useful tool to apply in Cloud Compare. I already tested it just before this lecture. So what you can do then is import your airborne laser scan point cloud, select your point cloud, go to plugins. In this case, we use the SCF filter. Okay, we have a steep slope. There are 3 types of slope. If it's flat, little relief or steep slope. This is quite a slopey area that we're talking about here. And here you can set the resolution. So that's actually related to the point density. In my case, I have, how much was it? 8 to 20 points per square meter. So I put it on 20 centimeters here. This is a matter of fine tuning, and this is also a matter of fine tuning. And then you press OK. And what it's actually doing now is assigning a class to points that belong to ground surface and points that belong to non-ground surfaces. It does it fully automatically. Of course, it's not error-free, so it's always good to have a look on the results, maybe fine-tune your parameters. And especially if you have a lot of variation, topographic variation in your point cloud, it might be useful to segment your point cloud first. So this is a point cloud of 6 million points. It takes, let's say, 30 seconds. And the result is that if I take my ground points that I have here, all my ground points automatically filtered. And I have the topography under my my tree canopy. So if I go back to my canopy, these are my trees, all these little clusters that I have here, and this is my topography. So just airborne filtering, if you ever have the ability to work with these data, it's extremely useful also for archaeological landscape research. Voila. That's about point cloud filtering. Do you have any questions so far? Are you still awake?
No, it was clear. Thank you.
Okay, let's have a little break. My daughter brought me some milkshake. Some more milkshake that I will have to drink, otherwise I have a fight here. So let's, I will close the recording. Back. I've started the recording again, and I will share my screen to give you just a few more notes on the deliverables. And this is actually the last part of the presentation for today. Do you have any questions about the previous presentation so far already? Then let's get started with the deliverables. So point cloud deliverables. Most of the time, if you're working with point clouds, you put a lot of effort on preparing your point clouds. You put a lot of effort on registration and preparing your filtering and or classification. That's most of the time, that's not the finality of the work, because the end of that process is of course a new point cloud, and most of the time people are not very familiar with it. You want some digital elevation models, you want some maps derived from after GIS-based data processing, architectural plans, and stuff like that. So I will just give you some notes on that topic. So after cleaning the point clouds, registering it, cleaning it, archiving it, filtering it, segmented it, then we have to continue our work. And then we're actually here in this segment of the processing. So the deliverables of the project itself are frequently defined by the project owner. So the project owner, he will say, okay, I want a point cloud, I want rendered images, I want animations, mesh, 2D or 3D drawings, decimated meshes, or something like that. And that's what we have to work on. Of course, we do all our processing on its point cloud registration. We covered that. And if you're working on point clouds, or the point cloud is the finality of your project, you can of course use these different values attached to each and every point for point cloud visualization. So for example, you can say, okay, we're interested in classification values. So I want to visualize my point cloud as a function of the class that is assigned to each and every point. We can use depth values, the distance from a reference surface or from the scanner itself to the object. RGB values, so just make colored point clouds for visualization, and that's actually what we're going to do tomorrow, or intensity values. So if you want to work with point clouds, most of the time you will have something like that, just simple screenshots, or an interactive viewer in a browser that allows you to have interaction with the point cloud. Let me go back to the point cloud that I have here, like in this viewer, and I will go into a little bit more detail about this tomorrow. You have the ability to measure distances. Voila, distances here, define points. Voila, let's measure a distance from here to here, for example. And this is directly in the point cloud itself. But most of the time you will not work with these kinds of applications. And most of the time then, in that case, you will combine your data with color information, also something that we already discussed. So you will not only use the geometry of your point cloud, but also the information attached to each and every point. And then using these point clouds, you can actually derive some interesting primitives or interesting topographic features out of it, like as I also demonstrated in the point cloud of the Flemish region, like topographic artifacts. If you're working with point clouds, and if the point cloud is a finality on its own, then again, you will have to decide on what format is required for data interchange or data exchange. You can say, okay, we're just going to publish everything in the native scanner format. That is very useful if the project owner or the people that will use your data have the ability to use that software. But most of the time that's not the case, especially in interdisciplinary teams. You will experience that people are not always very familiar with point cloud processing software. And in that case, you will have to work with open data formats like ASCII-based or open binary formats, like as we also discussed yesterday. The big advantage of these online interactive tools or interfaces is that you don't need additional software. You can just load the point cloud in your browser. You only need Chrome or Safari or anything like that, and you can have your interaction. And of course, most of the time, you can also get some useful impressions using screenshots or animations. I think I have an animation from 2007. Let me go there. A fly through made by a Spanish guy. I think it was in 2017. Animations. So for example, here, an impression, a fly through of a point cloud in Navpio. So we're going from the 3 Admiral Square in the direction of Syntagma Square. Go to Syntagma, voila, here we are on Syntagma Square. And we're having full, the full point clouds that we can show doing that. But of course, there's no interaction. What you see is what you get. So the developer of this movie, this Spanish guy, he made the path, and the path was used for point cloud rendering. So very useful to get an impression. You only need some video software to visualize it. You can put it online for further for sharing your point cloud. But it is impossible, of course, to pause it, do some measurements, or do some further analysis on the point cloud. And of course, yeah, tomorrow for the online point cloud visualization. If you want to do a little bit more on the point cloud and make it the data more accessible, it is always good to think about GIS or CAD compatible deliverables. So for example, if we are working again with these airborne laser scan data from the Flemish region, and I'm talking about the region of Maasmechelen, this Second World War site, or First World War site from the Agency of Information Flanders, or Information Flanders, we can use Cloud Compare to do some, or to generate some more complicated or more advanced deliverables like meshes, digital elevation models, pseudo-orthophotos, or cross sections. And that's actually what I'm going to show to you here. In this case, it is very important again to mention that a priori Cloud Compare is only able to generate 2.5D meshes. So full 3D meshes are not possible. There is one way of making full 3D meshes, that's the Poisson surface reconstruction, but especially for highly detailed artifacts, that's not very convenient. There's a question. Okay, see you tomorrow, Vasya. And enjoy your day. I hope to see you tomorrow then.
See you tomorrow. So.
Yeah. Thank you for letting us know. So we can use Cloud Compare to make these 2.5D meshes, and I will show you how. If I have, yeah, voila. So this is my point cloud, the ground points that I just filtered using this plugin, CSF, the CSF filter. I have my point cloud here, and I want to do something with it. I want to make a mesh out of it. In that case, I click on my point cloud, I go to Tools, and I click on Edit, Mesh, and I say Delaunay 2.5D or XY plane meshing. And it will actually calculate a flat surface or a horizontal surface where all the triangles are just projected in our horizontal plane. So it's a flat mesh that we have here. The interesting thing about this mesh, although it's extremely heavy for further processing, but it is possible to select this mesh and then export it to some 3D object. One way of using this technique is that when I was working on the globe, the Mercator globe that I also demonstrated to you in the previous exercise or the previous module, I had a globe with a very complex geometry according to Agisoft. What I did, I extracted these points, I put it in Cloud Compare, and I fitted a sphere on these points. Then I took the sphere from Cloud Compare, I imported in Agisoft, and I actually had a very simple geometrical representation. So for data reduction, this can be quite useful. But in this case, yeah, I have a 2.5D mesh that I can use in Sketchfab or in Blender or 3D Studio Max for further processing. So that's my the mesh that I have calculated here. A more convenient way to work with Cloud Compare for the extraction of GIS-based deliverables is the extraction of digital elevation models. And in that case, I will take also my point cloud. So let's take my point cloud. I'll close this one and visualize my points again. Voila, there they are, my points. By the way, if I want to visualize these points as a function of the altitude, I haven't showed to you that far, or so far, I can select my points and then I go to Edit, Colors. If you go to High Ramp, you can just press OK, and now I have a color as a function of the elevation of each individual point. But it's maybe easier to do a point cloud interpretation using a visualization like that. But still, we have here our 4.3 million points, and I want to generate a digital elevation model, and that the digital elevation model, I want to use it in QGIS for further data processing. So let's go with the point cloud selected to Tools. I go to Projection, Rasterize. So Tools, Projection, Rasterize. I can set my resolution. So let's say, for example, I want a resolution of 25 centimeters as a function of the height value in this case. And I will press Update. Yeah, voila, there we are. I only see red values, and that's because of the fact that my no data value is extremely low, so don't worry too much about it in this case. So my resolution, my height, my active field, so my elevation, I want to put in my digital elevation model in the direction of my Z direction, my Z direction, using the average value per cell. And if there's no data available, I will just perform an interpolation. And if it's outside my scope or outside my my area, so I have to extrapolate data, I will just assign a very low value to that digital elevation model. Still in this screen, I go to Export, and then I can say, okay, raster, what do I want to export? Well, my height value. Let's export my height value, and then I can save it, DTM Maasmechelen, for example. Voila, and now I have a DEM. Let me go to my desktop. I have here a DEM entitled DTM Maasmechelen, and this raster can then be imported in, for example, QGIS. I don't see anything because, of course, I had to first set my coordinate reference system. I'm working in the Belgium system in this case. I retake my DEM. And now the only thing I have to do is set my no data value. Allez. Reset it a little bit. Let's go a little bit higher. A bit more. Not a bit more. Voila. And now here you see my digital elevation model. Modify the colors if you like. Something like this. Still not very happy. Voila, and here are my colors. as a function of the altitude in a digital elevation model. And even now you can clearly see the topographic deviations that were originally not very visible, not clearly visible in our original point cloud. So that's on the extraction of digital elevation models. Important here is to set your step size. So the step size is actually referring to the resolution. The size that you see under that value, let me go here, is the dimension of your resolution. Sorry, the dimension of your raster. So in this case, I had a square, and the square has a dimension of 2001 by 2001 pixels. I use my elevation values here, but I can also use, for example, my RGB values. If I do that, I will actually end up with an pseudo orthophoto based on the colors in the Z direction. So let me export this as well. RGB Maasmechelen. And I hope this works. No. Now, of course, because I first have to set my my color value here correctly. It's just taking the projection of my my value. So if I have this value here, I'm sorry, I will go back, projection, rasterize, 25 centimeters. My RGB values, I will interpolate if there's no data available. And if I export this, export RGB, I will override the result. And now here I have a TIFF file that is normally correctly aligned with my original digital elevation model. And this is actually a pseudo ortho, let's call it a pseudo orthophoto or orthophoto if you want, of the same area extracted from a point cloud with a resolution of 25 centimeters in this case. So now we have our DEM and we have our orthophoto extracted from point clouds. This is quite cool for further and useful for further data processing. So digital elevation models and orthophotos are all possible. I also explained you on how to use cross sections. So these cross sections can be very useful if you want, of course, not only for point cloud visualization and point cloud filtering, but also if you just want to have some sections, some horizontal sections of a building, for example, and you want to digitize the walls of a building in CAD software or in BIM software. In that case, what is very useful to do is that you say, for example, okay, I will go back to my Lierde data set. Let me take the entire point cloud. And what I will do is I will make a section, a cross section using this tool here on my point cloud. This is obviously not filtered. So let me take the Z handle a little bit downwards. Focus a little bit in the different directions. This is another reason why it's very useful to do some point cloud filtering, of course. Because this is not a very convenient way of showing what I wanted to show. Take back the handle, remove my ground surface. For example, like this, a little bit like this. And the result, what you see here, is actually a cross-section of all the different walls in my point cloud. Apparently I have the roofs of the building. So I will just put it a little bit lower, like this and like this. And now I actually have a profile of all the buildings, a cross section of all the buildings. And this is something, of course, that you can save or extract and then save and then say, okay, I just want this portion of the point cloud exported. Eventually, you can also do the connected component analysis here to get rid of all the noisy data, import it in your CAD software, import it in your BIM software, and you can start drawing the contours of your building with all the detail that is still incorporated in the point cloud itself. So quite an interesting way also to work with your point cloud in Cloud Compare and use it in combination with CAD or BIM software. And then last but not least, also the ability, of course, to make profiles that you can export as a DXF. Is also something that I already demonstrated in last Saturday. The ability, if you have your cross section, that it will draw a line around your section, a polyline in this case, and this polyline can be exported as a DXF for further processing in CAD or BIM or even GIS software. By the way, there was a question the other day. I think it was asked via WhatsApp. The only thing that I demonstrated so far is the use of cross sections using this tool. However, it is also possible to extract sections along a polyline. That's the tool that you see here. And this is very convenient if you have a certain path, for example, and perpendicular to that path, you want to extract your lines. So I must be very honest, I'm not very familiar with that tool. So I will try to experiment with it in real time. So let me take this tool, zoom in a little bit. And let's say we want to make a cross section of the roof here. Like this, for example. And then in this case, we can say, okay, generate orthogonal sections along the path. What's the SEP size? That's the distance between consecutive sections. And what's the width? How many meters on the left side and the right side should I consider? Let's take 5 meters and a step size of also 5 meters. And if we press OK, it will actually generate my lines. And then I can say, okay, extract points along the active cross section. And then normally, if it worked well, I hope it did, then here are my my sections. Apparently here there was an undercut because of the room that has been measured inside the building, but this is actually quite a nice cross section of the roof of that building. But once again, this is a live demo. It is not always that successful, apparently, because in this case I have measured also, or I've considered also the interior space of the building, and I was not inside the building, of course. But just for your information, this is a way to draw lines through an archaeological site on a path, or just have a free polyline perpendicular on that polyline. You can extract your profiles or your cross sections, as you would say. So that's what's expressed here. So let's continue a little bit about the use of QGIS. I already imported my digital elevation model here in this instance of QGIS, and a very interesting way of perform topographic enhancement. And now we are talking about airborne laser scanning data, but obviously if you have a facade, so let's take, for example, this building here. I will take this size, this side of the building. I'll make a section of it, I'll segment it inside. So let's take this one. What you can do in that case, if you want to make an orthophoto facade model or a DEM of this facade, in that case you can select your segment, and this is a very good way to level our point cloud. So 1, 2, 3, and now the facade. We'll eliminate the rest of the point cloud. 1 to 1. Have to do it again. Tools, level, 1, 2, 3, 2, 3. So now it's in my horizontal plane. I will rotate it a little bit around the Z-axis. So let me do that. Now let's assume that this is my correct facade. And what you can do then, assuming that my facade is now projected in my horizontal plane, I can go again to edit, to tools, projection, rasterize. And here I can say, okay, let's make a digital elevation model of my elevation values. I'll leave this empty. Voila, and here I have my my digital elevation model of this facade. Of course, normally you would do it more carefully, select your points more carefully, but this is an interesting starting point, and you can actually export this this DEM and use it for further data processing in GIS or in a CAD environment. Modify the resolution, etc., etc., and then you can start digitizing it here in it. Something that I didn't express that far and that I'm going to tell you about in QGIS is working with hill shades. So a hill shade is actually an artificial light source that you will project on your surface, and it will actually generate this pseudo shading of the object. This is obviously not working very well here in this case. I don't know, most probably because there's still artifacts here. So let's go to QGIS, take our DEM, and assume that we want to project our object with a hypothetical light source. In the processing toolbar, we type in hill shade. Let's go to hill shade. We select our digital elevation model. And Z factor is actually an exaggeration value that you can assign to your digital elevation model. So if the micro topography that you want to measure or the artifacts that you want to see in your facade plan are very small in relation to the rest of your object, you can increase this value. I will not do that here. The parameters of the illumination. So what is the azimuth of your artificial light source, and what is the angle, the vertical angle, or let's say the height of your light source, and then here you can set your output file. I will leave it on temporary, and then here in this case, because of this no data value, of course, there's some errors in the data. Demonstrations are not working very well today. I'm very sorry for that. I will take another digital elevation model to show it to you. Let's take something from Romania. So this is my digital elevation model. And with hill shading, let's consider the same parameters. You can actually make some kind of a hypothetical shade on the model itself. And in many cases, you will see, especially in topographic maps, you will see this as some kind of a background map. Especially, for example, if you buy a topographic map in Germany, for example, you will frequently find, or in France, you will find these kinds of hill shading on the topographic map. For example, what you see here, this is Open Topo map. There's also an artificial shade projection projected under the topographic information of the map itself. And for example, if we then have our hill shade and we take our orthophoto, here's our orthophoto. If we put the orthophoto under the hill shade and we play a little bit with the transparency, so let's put the transparency on 50, you can actually get quite interesting visualizations of your terrain, the true color information and the artificial shades. There are some other tools that you can use as well. So normally, if my live demonstration would go well, you will see something like that. But because of the parameter referring to this very low minus 9,999, the result is a little bit less convenient. But normally you will end up with something like this. The problem with hill shading, and I'm really going into the domain of GIS, the problem with hill shading is that objects that are parallel to the direction of your illuminator, that these objects are not visible. So in this case, we had, let's go back to our parameters. We had a sun or an artificial light source in this direction somewhere at a height of 40 degrees. So it means that all the objects that are in this line, so in this diagonal line, that they are not visible. We can show that clearly if I take my DEM again and I'm pointing in, let's say, 30 degrees. So let's take a horizontal angle of 30 degrees. Now I'm actually projecting more or less in this direction, and you see that the artifact that I had, so here this slope or gully that I have here in this direction is less visible compared to my previous hill shade. In order to prevent these difficulties, a very interesting function to use is the sky view factor. The sky view factor is actually a parameter that will calculate a certain openness of your environment in all directions. So for radiation analysis, heat island detection, and omnidirectional microtopography enhancements, this is a very useful technique. It's of course more computational intensive. So compared to hill shade, you saw that hill shade calculations went very fast. It's just a matter of seconds and I have my results. If I go to sky view factor and I calculate the same, it will take a little bit longer. So let's just take the default values here. It will take a while to calculate it. So I will do my talk. But this is actually, as you can see here, a parameter that will define some kind of an openness related to a certain topographic position in all directions. That's quite useful. Oh, it's already all, so that's good. If I go here, no, and I take my sky view factor, let's take the simplified, then I have my topographic enhancement in all directions. So this is definitely a very valuable parameter for topographic enhancement techniques based on digital elevation models and especially based on DEMs derived from laser scan data. So very useful also here. I was originally going to demonstrate it to you. This is the hill shade on the right-hand side of the area in Maasmechelen in Belgium. And on the right-hand side, you have the sky view factor, where you can clearly very, very good visibility of the different military artifacts that are still occurring there in the current landscape. So for micro topographic aberrations, this is a very useful technique. And also, I gave a very short introduction to this in the previous specialist course, the extraction of profiles using QGIS. So this is something you can do in Cloud Compare, but if you don't feel very comfortable with Cloud Compare, you can actually also use profile calculation in QGIS. So what you do then is you go to plugins, because it's by default it's not installed. Plugins, then you look for profile and install the profile tool. If you're interested in this, I will send you a link where you can find some more thorough information. So profile tool, and then you will have this button here, terrain profile. If you click on it, then you select your digital terrain model, you add it to your library. You can add multiple digital elevation models. And then what you can do is just draw a line, for example, from here to here, and it will give you a profile. If you want to say, okay, what's the depth of this area here, you can just go over your profile, see where the point is, and then measure your elevations and or your distances on the X and on the Y axis. These profiles, by the way, it is possible to export them as graphics, so simple graphics, a PNG, but also as layered graphics, or even DXF for further processing or further fine-tuning in AutoCAD. But also the ability to export your profile as a table, a CSV file that you can then process in Excel, for example. If I go to Excel, then voila, here's my my profile, and I can easily make, in this case, let's say a scatter plot. So for publications, you have the ability to make your own profiles, fine-tune them, style them, and even if you're like in Python using matplotlib, very easy to make your own cross sections like that using this profiling tool in QGIS. So voila, import, assign your DEM to the tool, and then export this as a PNG, a SVG, or in CAD data. So last but not least, also mentioned by Michele, if you have your point cloud cleaned up and registered, it is important to mention that it is of course also possible to digitize your point cloud in CAD or in BIM environments. If you're using CAD, and more specifically, if you're using Civil, there's a cool, thank you very much. If you're using Civil, it is also possible to import your point cloud. But if you want to import your point cloud, and especially if you want to import your point cloud and you're affiliated with a research institute or an educational institute, you will have to use recap first to convert your point cloud. This was not in the original presentation, but if you install Civil, most of the time it also installs Autodesk Recap. It's also a software package for point cloud processing and for photogrammetric reconstructions. And if you have this software, you can also do some registration, some point cloud filtering, but just in an Autodesk environment. And using these data, it is also possible to make a link between these data sets and AutoCAD Civil. So voila, we are now in the 3D viewer of Revit. Revit Recap. You can export these data sets and then import them in Civil 3D to draw your plans, your walls or constructions. And also in Revit, Autodesk Revit, it is possible to make a link with these point clouds. It's our RCP extension, I think, if I'm not mistaken. And then using these point clouds, you can also extract buildings, walls, cylinders, and other stuff like that. So just to wrap up this session, once again, if you want to work in Cloud Compare and QGIS, most of the time you will really have to consider or take into account that you're actually working with 2.5D data. So if you have a full 3D scan of an environment and you want to use Cloud Compare and QGIS in combination of each other, you will have to project your facade, you will have to work with airborne laser scan data, or project your facade in a horizontal plane, and then you can start modifying, drawing lines, making your hill shade, your sky view factor, or digitize your object. Of course, in a 3D approach, Cloud Compare is very suitable for point cloud registration and point cloud filtering. I think that's obvious now. But for the real deliverables, I think there are better software solutions that are to date still commercial and potentially quite expensive. So Cloud Compare 2.5D for deliverables, but if you want to work in 3D with point clouds, so I'm not speaking about 3D geometrical representations that you would make in Blender or in other 3D modeling software, but really on point cloud with millions and millions of points, I think you will have to go to software like Cyclone or Leica Cyclone or RealWorks from Trimble or Scene CS from Faro. Voila, that was about point cloud deliverables. The pre-last session already. And tomorrow we will talk about the publication of points using online servers in JavaScript. Do you have any questions?